Ladies and gentlemen, welcome to the last lecture in our series on Earth Sciences. Today we are going to talk about volcanism. In Marschall's textbook you will see relevant sections on volcanism in chapter 6 and in chapter 9. Please have a look at the respective sections. Where and how do volcanic eruptions occur? Where we will find them? We will see that volcanic eruptions are not randomly distributed over the planet. And here we see a map that highlights volcanic centers on Earth. You see here these little triangle symbols that shows the position of major volcanoes on Earth, and you see here there is a linear concentration of them along the American west coast, North America and South America. Also here at the east coast of Asia, of the Asian islands and the Asia mainland, we find lots of volcanic islands and volcanoes on mainland. Also here in Indonesia there is a chain of volcanic islands. Volcanic eruptions also happen at the sea floor, and here again in linear arrangements along the mid-oceanic ridges at positions where new oceanic crust is formed. Here in the Eastern Pacific we find a network of such volcanic chains, also in the Atlantic from south to north all the way up. Iceland is a volcanic island in the northern Atlantic, and also here we see a connection into the Indian Ocean that would continue over here. So in the middle of the oceans there is major volcanic activities and along continental margins, specifically here around the Pacific. In other areas we find volcanic activity here, specifically in the East African Rift. Here we know that the Somali plate is in the process to separate from the rest of the African plate, and we find volcanism in southern Europe, specifically here at a margin of the main European plate with small plates further south. Hence we can see that volcanic activity is related to specific geological positions, and here we see them. Island arcs where oceanic lithosphere is subducted underneath other oceanic lithosphere. Here islands will form islands that are formed essentially by volcanic material. The Marianas here in this area are such an example, or also here Indonesia has a chain of volcanic islands that have formed in such a position. The continental arc is typically developed here in the western United States, and specifically probably the best example here in the central Andes and the southern Andes of South America. Rift-related volcanism obviously here in the East African Rift, and then there are others. There are hotspots. There are areas where randomly in the middle of plates volcanic islands occur. Hawaii is a good example for that. And of course the mid-oceanic ridges, as we have mentioned them all over the place in the large oceanic basins of the world. We are going to talk about these hotspots here in a minute. But first let's have a look at a piece of software that I haven't shown you yet. This will illustrate where volcanic eruptions and also earthquakes occur on planet Earth. This will correlate very strongly with this kind of distribution, but it's animated software and you hopefully will like it. Okay. So what you're hearing here is a rumble of earthquakes. A rumble of earthquakes, and you see earthquakes are also related to plate margins. Every little bump is an earthquake over a certain time. We are running here a sequence in the 1960s, and I stop that for now. So here we start again with a clean slate, and we are now looking at volcanic eruptions, and let's just set the cutoff relatively large. Here magnitude of 3, these are fairly large volcanic eruptions. Let's see what happens and where these volcanic eruptions occur. Again, we are starting in the 1960s with a time increment of 3 months per second. Kilauea, South America, South America. Aleutians. Kilauea again in Hawaii. Also here in southern Europe there is some volcanic activity. Let's increase the speed a little bit. 1 year per second. And you see again, volcanic eruptions are concentrated in specific areas. Also here in the East African Rift, there is quite a bit of volcanic activity. Southern Europe, Iceland, and again, the Hawaiian Islands. This software is free, you can download it from the internet. I can provide you with the connection, and then you can install it onto your laptop and have a look at volcanic eruptions and seismic activity in the earth. You can select specific areas and specific events, and you will find much more information about volcanism and seismic activity, earthquakes in this software. It might be a good thing to have a look at that. We are coming back to that in the mainstream courses in first year, and also then in second and third year to some extent. We have been talking about mid-oceanic ridges, and mid-oceanic ridges by volume extrude most magma on the Earth. It's just not that spectacular because it happens in deep under the sea in about 2,000–3,000 meters water depth, and we hardly ever see anything of that. We're going to see a little video a bit later where such underwater volcanic eruptions are filmed, and there you get an impression what happens there. This happens all the time, and the magma that is extruding there is essentially basaltic, and it is dry magma. You might remember it has formed by decompression melting of dry mantle material. So it will have a low gas content, and it is not very explosive. You actually can, with a submarine, go very close to such a volcanic vent and look at the eruption of this magma and its interaction with the seawater. Just a reminder here to the last lecture that we have seen. In mid-oceanic ridge environments, we find this quick deep compression that allows mantle material to hit the solidus and then undergo partial melting in fairly shallow depth of maybe a few tenths of kilometers, maybe up to 100 kilometers depth. Another setting that we have not yet discussed is that of a hotspot. In some places in the Earth there are positions where mantle material, hot mantle material, rises from the outer core mantle, lower mantle interface in something that we call mantle plumes. This is hot, low density material that rises very quickly throughout the mantle. It has a high temperature, and when it hits the bottom of the lithosphere, it reaches shallow depth and undergoes partial melting. And here there are large volumes of mantle magma produced up here. So melting again only occurs here at shallow level. All this rising material is soft, but it's still a solid. When we have such a situation that such a stable, in position, a static mantle plume hits a lithospheric plate that moves, and the Pacific plate, where we find Hawaii, the Pacific plate moves to the northwest, as we see here indicated with this arrow, we will form a chain of volcanic islands. Some of these islands are older, others are younger. Hawaii is at the position where the mantle plume hits the bottom of the lithosphere currently, and other islands here like Maui, for instance, and Oahu, These are islands that used to be at the position where the mantle plume hits the lithosphere. But in the meantime, the Pacific plate has moved on and has transported these islands away from the plume. So these are no longer volcanically active. Here we see that in a sequence of time, a hotspot is at a specific position, a plate moves over it, and where the plate just happens to be, or at the position that is on top of the plume, there a volcano will form. Then the plate moves on and the volcano gets extinct because it's no longer on top of the plume. And another volcanic island will form in a chain that successively becomes longer and longer. We see this process here. And that is exactly how the chain of Hawaiian Islands has formed in the past. Volcanic eruptions in such environments are not very violent, but they are usually very active because you have a constant supply of heat, and this constant supply of heat produces and generates a constant supply of magma that is fairly hot magma. It often extrudes in such fissures, but it does not produce a lot of ash, because for ash you would have to have a lot of gas and fluid in the water. These are fairly dry melts, and they are fairly harmless. They flow out, they pour out at the surface. Their direction of flow usually can be predicted, and that means these are fairly easy to manage volcanic eruptions. No big surprises for humans living on such islands will come from such eruptions. So here you see they form large layers of basalt. That's what we call plateau basalts, and they consist of huge volumes of basaltic material. Here we see a map that shows us such hotspots. Hawaii is only one of them. There are many others. Pitcairn, Easter Island, Louisville, Samoa. These are only some of those. Or Galapagos Islands, of course, are quite famous. These are only some of them in the Pacific. You see also here Tristan da Cunha in the Atlantic, St. Helena, Réunion, the Caguelas Massif, the 90 East Ridge here. All these are chains of islands or submarine volcanoes that we know on Earth. Also on the land are a few. The Afar hotspot is one of those, and here in North Africa are a few others. So there are quite a number of mantle plumes active today or in the recent past that have produced massive amounts of volcanic material at the surface. So again, all of them are related to decompression melting. Here is an example of how the lava looks like at the surface, and here you see the photograph from Hawaii, where there is here an eruption center, and away from this eruption center, lava flows in river-like channels, pouring out over the landscape. All the landscape here is formed by older basalt from earlier eruptions. The low gas content is the reason why such volcanic eruptions are not very explosive. You just see the outpouring of liquid lava at the surface. It's quite a spectacular view, and it's not specifically dangerous. You can go fairly close to such eruptions, and that is something that is not so for other eruptions. We will see that a bit later. Here's another photograph. It's very, very beautiful to look at. The hot lava has a temperature of about 1200 degrees. It starts here to cool down and solidify. You see here a crust, a solid crust is forming that is perhaps something like still 900 or 1000 degrees hot. But obviously with the distance of the volcanic center, this lava will cool down and it will end up as basaltic material as you see it here in the surrounding area of this lava flow. Another photograph. You find quite a few of them in your textbook. At a larger scale, these hotspot volcanoes form large plateaus. You see volcanic centers in specific places, and from these volcanic centers you find layer by layer outpouring magma, growing the thickness of this of these volcanoes, of these plateau volcanoes. This is a very different shape of other kind of volcanoes that you might have seen and might have heard of. We will come back to this other type of volcano a little bit later. These plateau volcanoes, they are characteristic of hotspot mantle plume related volcanic activity. Here we see one in nature, and this is what we call here a plateau or a shield volcano. Here you see that large lateral extent. They can be fairly high, they can be up to 4,000 meters above sea level, but because they are so large, they don't have very steep slopes. This is pretty much resembling the sketch that we see down here. That is what a shield volcano would look like. Now we are going to look at two more video clips. One comes from Hawaii. It shows us the volcanic eruption on land, and we are going to see undersea volcanic eruptions in a similar kind of setting related to mid-oceanic ridge spreading. So here we see a video from the Hawaiian Islands and the outpouring of lava. Here we see an interaction between hot lava and seawater. We see here it's close to the sea, and in the underground there is quite a lot of water. This produces a lot of steam that we see here in white. Let's have a look at this video. This is all water steam. This is at night, so you can see the lightning a bit better. The lightning forms because the ash particles in the air, they have an electrostatic capability, and so you charge the air until you actually discharge in form of lightning. So this is a very similar effect like it might happen in a thunderstorm, where you also have charged particles discharging in form of lightning. Let's have a look at the next undersea volcanic eruption.
Hi, my name is Joe Reesing. I'm at the Joint Institute for the Study of the Atmosphere and the Ocean at the University of Washington. I was the chief scientist on this expedition, so I led the intruders and the tricks of the eruption. The video that you'll be looking at is large magma bubbles. They're about 3 feet across, and the bubbles are molten rock that are expanded under the pressure, gas pressure, of magmatic gas. And the magmatic gas, we presume, is mostly water, and when the water is under the magma, that's magmatic temperature south of the degrees, and when it's suddenly cooled by coming in contact with seawater, the bubble bursts. What excites me the most about this volcanic eruption is that that on planet Earth, this is a process happening all the time, and yet we have never seen it happening in quite this way. The ocean floors are formed almost exclusively by volcanic activity. And strangely enough, we really have never seen molten lava flowing on the seafloor from a submarine volcano. We have seen in other eruptions much shallower in the ocean, but in this case, we're actually seeing molten lava flowing on the seafloor. We're seeing these magma bubbles, we're seeing these explosive events, we're seeing the seafloor open up and pour out magma. We're seeing these pillow lavas, probably one of the most common forms of rock on Earth. And despite the fact that this happens, 80% of the volcanoes, 80% of the eruptions basically on Earth are happening underwater. And we've never made these observations before.
The original video files will be made available to you as separate entities. So now let's have a look at a different style of volcanic eruptions, those eruptions that are related to subduction zones, where we generate melt not by decompression melting. Here we are generating melt by the hydratization of the asthenospheric mantle, and the fluids, the hydrous fluids that are required, are released from mineral breakdown in subducting oceanic crust in about 100 kilometers depth. We have talked about this process in the previous lecture. In such situations you will form chains of volcanoes in the overlying plate, and very often this is a continental plate. You see here the lithospheric plate with continental crust on top. This would be a situation that we see, for instance, in the Andes, but also in parts of the Philippines. Let's have a look at the Andes. The situation is here that a part of the Pacific Ocean, which is called the Nazca Plate here, migrates to the northeast at a fairly high speed of 13 to 16 centimeters per year, and the South American continent is moving in opposite direction. That forces the Pacific Plate, or the Nazca Plate in this case here, to subduct underneath South America, and that forms the Andes, and with the Andes a chain of active volcanoes. And we are going to have a bit of a look at the landscape and the volcanoes that form in this region. We are going to talk essentially about an area here in northern Chile, in the vicinity of the border to Bolivia and to northwestern Argentina here in this region. All the photographs you are going to see come from this area here. So that would be our playground. Here we see the area in a close-up. In a satellite image there is the town of Antofagasta, and this is the Atacama Desert. Calama is a small village in the Atacama Desert, provided with water from the high Andes, from over here on long pipelines. And Calama exists only because there are large copper mines in this region. The copper mines, this is the largest copper province currently on Earth, and all the copper is produced by volcanic activity in the past and is now at the surface and can be mined. Here we see one of these mines. This is the currently largest copper mine at Chuquicamata. We see here the pit, we see here the facilities and the processing plant. Here is a large dam that is required to process the copper. And here is the city of Calama down here. Let's have a closer look. This scale here is 11.3 kilometers. Having a look at the pit itself, you see here the pit is about 4 to 5 kilometers long and more than 2 kilometers wide. It is a huge open cast mine in the middle of a desert, producing a lot of copper and also some silver and gold. This here is also from the Atacama Desert, but as you see here, this is not the desert itself. That is the oasis of San Pedro de Atacama. There is a little bit of water coming from the higher Andes, and in the background you see in the haze the first high volcanoes. These are volcanoes almost 6,000 meters high in altitude at the border between Chile and Argentina. Again, here we see on the San Pedro Plains, now outside of the oasis, a chain of volcanoes. Here all these are volcanic mountains, and the spacing between them is about 70 kilometers. It looks a bit hazy, but in fact the air is very clear here. This mountain is about 150-200 kilometers away from the position where the photograph is taken. On the high plateau we see here two beautiful volcanoes close to the Laguna Verde, which is quite a tourist attraction there as far as tourists come up there. This here is the Licancabur in northern Chile, and this is a volcano called Juriquez. We see them here from space. The Juriquez has this flat top, which when you look from above you see is a large volcanic crater, a collapse of a crater after volcanic material has poured out of the volcano. The Licancabur does not have such a collapse at the moment. It might develop a collapse structure, a crater in the future. And here you see from top this beautiful conical shape that we see here. And we see also that here are several lava flows that have poured out from Licancabur and also from Juricus here in the past. Licancabur shows the younger and better preserved ones, but there are even better ones in the region. This is again the Licancabur, where you see highlighted lava flows of different age. This, for instance, here is running over that one. That tells you that this here is a younger flow compared to that one. But here the Siricabur shows that even in a better way. Here is the volcanic center. Here are the youngest flows. They are pouring out here. Here are older flows running over an even older one and another one that is even older. Here in dark color, again a fairly young one. The color changes with the intensity of weathering. So here these old lava flows have been exposed to weathering a bit longer and they are getting bleached, and dust particles might settle on them. That changes a bit the color. And here the young ones, they are still fairly dark, as it is typical for the basaltic and andesitic lava that is formed in these regions. Here is another volcanic crater. Also here is another crater of a neighboring volcano. You can see here the scale. This is 1.3 kilometers. This is a not very large volcano, but there are just very, very many of them forming in the magmatic chain on top of the subduction zone of the Nazca Plate. So the Nazca Plate at these regions here would be about in 100 kilometers depth. That is where the minerals, the water-containing minerals, break down and move into the overlying mantle and generate the magma at depth that reaches the surface here in the volcanic chain of the Andes. A few more photographs here. The volcanoes on the high plateau. The high plateau of the Andes is about 4,500 meters altitude. That would be here the lowland. These volcanoes are about just under 6,000 meters in altitude. Also here you see beautiful salt lakes forming at the surface. It's a wonderful area. Very intense colors, very clear sky. So the sky up there is really that deep blue because you are very high in altitude, and there is very, very little dust and haze in the atmosphere. If you travel a bit further, you come into more vegetated areas. People are keeping llamas in the area as domestic animals, as livestock. And there is also a lot of wildlife there. Here, this is the non-domesticated equivalent of the llamas. They are called vicuñas, or also alpacas are a different form. You might have heard these names of these animals, very nice animals. The llamas are fairly tame. You see here they belong to someone. Somebody has tagged them with beautiful tags. And they are very curious. They always want to have food, but the problem is they are very, very smelly, so you don't want to get in touch with them too close, at too close up range. Back to the volcanoes. The volcanoes in the Andes often are very violent, and that is because they are fairly gas rich. Because in the magma there is a lot of dissolved water, you will have an explosive effect if this water dissolves again. At great depth, where the magma is generated just on top of the subduction zone, the pressure is very high. But when you decompress that magma and you bring it to the surface, you will have the same effect as if you open a bottle of Coke, for instance. If you shake a bottle of Coke and you open it, then the dissolved gas, the dissolved CO2 in the Coke will form bubbles, and you will get something like a small explosion. And at much, much larger scale, this happens with the dissolved water and CO2 in volcanic magmas. So these magmas can store and can keep the gases dissolved at high pressure. At low pressure, they can't do that anymore. And then an explosion happens. Then you see this massive disruption of the lava into smallest particles, which is then called the ash or tephra. And explosive ash clouds can rise far into the atmosphere, or they can run down as pyroclastic flows, as massive ash clouds down the slopes of such a volcano. And the continuous outpouring of such lava, ash and gas mixtures, that forms the typical conical shape of such stratovolcanoes. These debris flows form here layer by layer by layer, obviously the oldest one at the bottom, the youngest ones at the top. Another name for these pyroclastic flows, for the ash clouds here, is a French term, nuée ardente. Nuée ardente is a term that you might come across when you deal with literature on volcanic eruptions. And we see here the situation, again a magma chamber at some depth that can be within the crust, that can be at the bottom of the crust. And here these gas-rich magmas are transported via a conduit, via a channel to the surface and then into the volcanic environment. I'm not going to talk about all these different terms that are related to describe volcanic features in the region. You will come back to that if you study geology. But here we see such a pyroclastic flow just forming in context with also ash clouds and gas rising into the atmosphere. We have seen this photograph before. These are these violent pyroclastic flows, or nuées ardentes, that are very violent and very dangerous. They are smelly too, yes. There are different styles of volcanic activity, and here they are shown in context and in comparison. There is a Vulcanian type, which is usually forming in volcanic islands in the sea, producing a lot of gas, of steam. There are the Hawaiian eruptions that we have seen in the video before. Then there are hydrovolcanic and strombolian eruptions and so-called Plinian eruptions. The Plinian eruptions are the largest scale, despite of the different size of the ash cloud here. This is a matter of scale. We will talk about these different types of volcanoes now in the following. Going back to the Hawaiian style, to the eruptions that are related to plume activity, such eruptions essentially form liquid basaltic lava that extrudes from such fissures, from such gaps, fractures in the earth, where they are ejected into the air. But we see here very little gas, very little ash, and we see essentially the red-hot glowing lava that then flows away in river-like channels away from such fissures, from such fractures where it hits the surface. The low gas content is the reason why it is non-explosive. There is little interaction with groundwater that, if it would get dissolved, would form immediately steam that expands rapidly and that would form a explosive nature. That is not the case with these Hawaiian style eruptions. Typically such eruptions can last quite a while, a few hours or days, sometimes even much longer. The lava flow is fairly continuous, and because the lava is very hot when it erupts, it stays liquid for quite a while, and in these larger lava channels it might actually travel kilometers away before it cools down and hardens and then freezes and forms a volcanic rock. The Strombolian style is slightly different here. Here you see the eruption of lava in bursts. These bursts are usually very distinct, relatively short events, and you see here that material is ejected far into the air. You see here the track of a lava bomb, which is a red-hot glowing particle of up to several meters in size that is thrown out of the eruptive center into the air, and here you see it quite nicely, the trajectories of such particles. Typically such eruptions are caused by the bursting of large gas bubbles that are traveling up the conduits. You must think this is just like a big burp. It comes up, and when it hits the surface it expands. This gas expands because it's getting more and more decompressed, and then ejects a lot of lava together with some gas and bombs and scoria, ash. These particles, these volcanic materials, are thrown out and this can be up to several hundreds of meters in the air, as we see it here. That is what we call a strombolian type of eruption. So this requires that the gas actually is already part of the lava, part of the magma that rises from deeper levels, from a holding chamber, and this is not possible in a Hawaiian style where we have lava that is depleted. It does not contain large amounts of volcanic gases. The next type of volcanic eruptions are hydrovolcanic eruptions, also called Surtzian eruptions, after an explosion on the island of Surtsey in 1963. When magma interacts with groundwater or with surface water, it will rapidly expand while it is converted into steam, and this conversion into steam and this rapid expansion causes massive explosions. You can say that these Surtzian or hydrovolcanic eruptions are a wet equivalent of Strombolian type eruptions. So take a Strombolian eruption, as we have seen on the previous slide, add some water, cause a large explosion. You will disrupt the magma into very fine-grained particles, and these particles are nothing else but volcanic ashes. If you have an eruption that produces enough volcanic ash, you will produce ash layers in the surrounding of the volcano, depending on amount and travel distance of these ashes. Such layers can even be found in quite some distance to the volcanic center. You remember on our field trip we have seen such ash layers at Eka Pass. Here you see the kind of environment where the ash was formed. And think about something like that in the time of the Permian, in volcanic centers not too far away from the Karoo Basin. This is the environment where these ashes were produced. Volcanian eruptions are slightly different. They are usually short and violent eruptions, but they are smaller explosions compared to those that we have discussed previously. Volcanian eruptions are related to a different kind of magma. This magma in Volcanian eruptions is richer in silica, and that makes the magma more viscous. So the flow is not as easy as we have seen, for instance, in a Hawaiian type eruption where the magma, where the lava flows almost like a river. In Volcanian eruptions, the lava is much stiffer because of the richness in silica. That increases the velocity. So what we see in these kinds of eruptions is typically the explosion of a plug of viscous lava that travels up a conduit. So if magma slowly moves up in a conduit and then gases expand, then you get a short, rapid, violent explosion. And what is typically produced in such an environment, these are gas and ash clouds. You see here a lot of gas. The color is much whiter than the ash clouds that we have seen previously here. Here we have essentially magma particles that form the ash. Here we see essentially gas. But you see also here a gas and ash cloud is running down the slope of this volcano. That is characteristic of Volcanian eruptions. And often some Volcanian eruptions are preceding larger explosions that might follow in the near future. And now we come to the largest and most violent type of volcanic eruptions, the Plinian eruptions. What we see here in such Plinian eruptions is the massive fragmentation of gas-rich magma. And these are usually associated with rhyolitic or dacitic magma, and these dacitic and rhyolitic magmas, that refers to the composition of the magma. These are also viscous types of magmas. What is characteristic for Plinian eruptions is that an enormous pressure has been built up in a subvolcanic magma chamber, and the high viscosity of the dacitic or rhyolitic magma that has stopped the gas to be released. It has stopped the magma from pouring out, and that allows this massive buildup of pressure. The eruption, the final eruption of such magma chambers and lavas usually produces massive ash and gas clouds that can rise up to 50 kilometers into the atmosphere, and they travel very, very fast, hundreds of meters per second. The huge amounts of ash that can be produced by such a Plinian eruption can drift with the wind hundreds of kilometers and even on global scale. And large volcanic eruptions are known to have changed the climate worldwide temporarily. There have been incidents where there were the so-called years without summers. Years without summers have occurred in history, and they couldn't be explained in, for instance, the Mid-Ages, but they usually caused massive starvation in large parts of the world, simply because the sunlight was prevented to reach the Earth by ash clouds in the atmosphere. You couldn't necessarily see this, but the insulation of the sunlight can be reduced by ash particles finely distributed in the higher parts of the atmosphere and the stratosphere, and that can have a very significant impact on climate, on regional climate, even the worldwide climate. Therefore, Plinian eruptions are certainly the most significant and globally most significant geological processes that regularly happen on Earth. Plinian eruptions are named after a Roman historian, Pliny the Younger. He reported on the destruction of Pompeii and Herculaneum, two cities at the foot of Mount Vesuvius, which were destroyed by such a massive volcanic eruption. These eruptions are extremely destructive. They will obliterate not only the landscape nearby, they also destroy the volcanic edifice itself. So the whole mountain can actually be blasted away by such eruptions, by such explosions, and this obviously transfers massive amounts of material laterally and vertically, and large-scale ash falls, scoria, lava bombs will impact on the landscape in a fairly large radius. The density of such pyroclastic clouds that move at high velocity, they can destroy forests, they can raze them, they can strip the soil from the bedrock, they can obliterate whatever is in their path. This is the large-scale Vulcanian type. So if you increase what happens in a Vulcanian eruption, you will get a Plinian eruption, but the magnitude is much larger in these Plinian eruptions of volcanoes. What is typical for these eruptions is that in the lava there is already quite some gas dissolved, and very often additional ground and surface water is added onto these explosions in order to increase their magnitude. Here we see a very famous explosion, also here on the previous slides that we have seen. Here we see the eruption of Mount St. Helens. This is a photograph taken from your textbook, but Mount St. Helens is probably one of the best documented volcanic eruptions. It was preceded by a number of indications that Mount St. Helens is about to erupt, and geologists have monitored very carefully what is happening in the build-up stage of pressure in the volcano. And finally the eruption took place on the 20th of March in 1980. This Plinian eruption was much more massive than expected, and the devastation was immense at that time. We see here the map that indicates what happened on 20th of March in 1980. Here is Mount St. Helens, a volcano of 2,500 meters altitude, and we see here in different colors different features that were formed in course of this eruption in 1980. We see here mud and debris flows, pyroclastic flows, the eruptive dome itself in the center, trees that were blown away laterally in following a blast that occurred here into northern direction. We see scored area and mudflow deposits, and then areas that were less affected and unaffected forest that had been out of the way of the impact and of the direction of the explosion. A lake has formed here as a result of the mass transfer in course of this explosion. Let's have a closer look. Pyroclastic flows are essentially seen here in northern direction of the volcano. The eruptive dome that has formed is here in the center. That is pretty much where the conduit is, and we see here the steep slopes of the volcano. A part of the volcano has blasted away here on the northern side. We see here gases and energy was released laterally, but essentially here in the northern sector of the volcano, where trees have been blown over and destroyed in a fairly large area. You see here the distance is about 3 kilometers on this scale here, and this here is something like maybe 20 kilometers away. So a very long distance, a very large area was affected by the pyroclastic flows and by the gas explosion related to the lateral blast that we see here. To the south, the area was much less affected. It was affected on a much shorter distance. Mud flows would obviously flow in all directions away from the volcano, but the blast was clearly laterally unidirected into northern directions. We will see how that happened and why that happened. Here we see over time the evolution of Mount St. Helens. There was an old magma chamber. Mount St. Helens was quiet for quite some time, but then a magma chamber was filled again with magma, and it expanded laterally here to the northern side and formed here a subchamber, which in fact lifted up the northern slope of Mount St. Helens. It formed what is called a bulge. The bulge responded just to the increase of magma volume in the subsurface, but fairly close to the surface. What then happened on 20th of March was that there was a vertical and a sideway blast when finally the gas pressure exceeded the strength of the overlying rock, and we had a vertical blast which formed a massive vertical ash cloud that would rise far into the atmosphere, and we had a sideway blast that led to the landslide and to a collapse of the whole northern part of Mount St. Helens. And it was this sideway blast that caused the massive destruction here in the whole northern sector of Mount St. Helens, with massive outpouring of gas and ash. Lava outflow was much less significant because this is a viscous lava. The destructive energy was released by essentially gas release. Here we see again this vertical and the lateral blast with the associated ash clouds, and in the following video that you please play as a separate file, you will be given that file. You will find much more impressive documentation of Mount St. Helens explosion. This is the end of our lecture. Thank you very much.